Good morning, everyone. It's a pleasure to be able to attend this conference online. Okay, I would like to thank the organizer for inviting me to share my research at this conference. The topic, the topic of my speech is about a problem of cybersecurity. Okay, this problem is not easy but interesting. Due to time constraints, I can only share part of my research today. In order to reduce the network traffic, I will turn off my camera. Okay. Okay. My outline is as follows. At first, I would like to introduce a defined cybersecurity problem. Then I will propose two possible generalization of this problem and show some possibility to solve them. Okay. Finally, is a conclusion. Okay. So at first, I would like to introduce the hierarchy of security issues. I think information security is the largest one. It is the practice of protecting information by reducing information risk. Later, we can consider the second layer called cybersecurity. It involves protecting an organization's internet connected systems from potential cyber attacks. And then it's the network security. Okay, it focuses on protecting an organization's IT infrastructure from online threats. In fact, it is hard to distinguish the cybersecurity and network security. So I give you this words description from the wiki, I think. So for the cybersecurity, I think its main object is to protect internet connected systems and networks. So later I will show you why this problem can be formalized as a graph problem. And usually for network security, it is to protect files and directories in a network. Okay, but anyway, we can see the other different views for these two kind level of security. Okay. So actually, this research is from these three papers. Or you can see it starts in 2016, and the latest paper is 2021. Okay, we can see they propose a model called a layer cybersecurity model. Okay, so what is the layer cybersecurity model? It's the problem, okay, given a tree T rooted at a vertex R, a penetrating cost H function C on T, a target acquisition vertex function P on T, the attackers budget B and the gain over ratio K. The problem is to determine the existing of a rooted subtree T prime of T within the attackers budget with total acquisition value more than the gain over ratio. In short, I give you an example why it called the layer cybersecurity model. Okay, so it's a rooted tree, So because we are given a root R, so we can distinguish vertex in the trees layer. Okay, level by level, I think. Okay, so in this problem, we are given two functions. One is C, the other is P. C is the cost function. It defines on edges. The other called the profit function. It defined on vertices. Okay, so if we can attack this subtree T prime, it means we have to pay the total cost here from this edge. Okay, and we can obtain the profits from these vertices. Okay, so this is the layers cybersecurity problem. Of course, with the cost constraint, we have to obtain the maximum profits. Okay. So now I first propose this called a possible generalization or a generalized version. Actually, you can see we can generalize this problem on graph. So it's a graph model. Similarly, we can define the cost function on edges and the profit function on vertices. Okay, so similarly, we are given a starting vertex called V. It means we can attack this graph from V. Okay. So if we can attack this subgraph G prime, it means we can obtain the profits. Okay. Summarized from vertices in this subgraph. The difficult part is how to charge the cost that we have to pay. So actually, we can see this is a kinetic component subgraph. So we can, if we want to attack this subgraph, it have to be connected. So you will see the minimal cost. Actually, it is defined on the minimal spanning tree of G prime. Okay, so now we know how to compute the cost that we have to pay if we want to attack a subgraph. Okay, so now we can define this generalized version called the decision cybersecurity problem. Okay, it's very similar to the previous one. However, it works on graph. Okay, so if our budget is large enough, of course, this problem becomes easy because the minimal spanning tree is the solution. Okay. So when it becomes hard, so at first we can see this one. If we sorry, I have to go to here to I have to mention again. So if the problem, if our budget is not enough, this problem become easy. However, our budget is never enough, so this problem is really hard. Okay. So I want to show you an example how to show this problem is very hard. At first, I show this problem in MP. So it means we can guess a certificate. Means a possible solution. Then we can verify this solution by applying Prim's algorithm. Okay, so we can check whether it satisfies the cost no more than B, and the profits we obtained is larger, at least K. So because Prim's algorithm runs in polynomial terms, so this problem is in MP. To show it is very hard. We need a reduction. Usually, we reduce this problem from an NP complete problem. It means we find a problem, NP complete problem, then reduce to our defined DCSP. Okay, this P means polynomial term reducible. It means if we can find this problem is A, okay, so its input, if we have a bread box, in this bread box, if we can find a solution, okay, then for B, then we can use the whole algorithm as an algorithm for A, and solve the problem A. Okay. So if we can do this reduction, then we show that DCSP is NP hard because this problem is harder than the NP complete problem. Okay. You also you can take an NP hard problem to reduce to this problem. Okay. So I give you an example. The 0, 1 naive problem is a very a classical problem in textbook. In this problem, we are given n items of objects. Each have its profit and its weight, and we are given a bag. That means its capacity. It can only hold 11 weights. Okay. Also, we want to know whether we can obtain the profit at least K. So for this problem, if we choose these two, okay, so the total weight is 11, and the profit is greater than K 36. Okay, so this is called the 0, 1 naive problem. So the reduction like this one, we are given an instance of the 0, 1 naive problem. Then we can reduce to our problem. In this problem, it's a tree. Okay, a tree is a very special graph. Okay, and we define its edge cost is Wi, and profit, this R is 0, and for each VI is PI, B equal to W, and K is the same K, and the vertex R is the starting vertex. Then we can, if we can find a solution for DCSP, then we can answer this 0, 1 naive problem. Let me give you an example here. This is 0, 1 naive problem instance. Okay, and we transfer here 5 vertices here, and the edge weights, it means the weight. Okay, the profit here. Okay, so if we can find a solution here, it means we can have we can attack this subgraph, and we take we pay the cost 11, and we obtain the profit. It's 40. Okay, so we make a reduction here. So we can show this problem is NP complete on star, because the tree is a very spatial. It's in fact it's a star. Okay, also we can say this problem is optimization version is hard on stars. Okay, so usually if you show a problem is very hard, then you you have to find some easy case. Okay, in this one, it's optimization problem called a maxima cybersecurity problem. We want to maximize the profit. Okay, so this problem we solve it on a pass because for a tree it is an NP hard. So we just consider the special case. Okay, so actually we can start from this one, the first vertex. Okay, because it's a pass, we can find this one as long as possible here. Okay, and we can compute the total cost we have to pay and the profit we can obtain. Okay, so it's easy, just a greedy algorithm. So we work we work all the way to right. Okay, so then we can compute the second one, take V2 as starting vertex. Also, we can find the total cost we have to pay and the profit we can obtain, and so on. We can do a similar process, and okay, and finally this one is here. Okay, this but anyway, I just want to show you this part show we can compute a possible solution in linear time because the total computation is linear. Okay, but anyway, we can solve this problem because we can find an VI to VJ. Okay, and this should be the best one. Okay, so so an optimal solution is a subpass. Okay, starting at some vertex VI and ending at some vertex VJ for this one. Okay, I should be smaller than J. So and so we can solve this problem in linear time. Of course, we can extend this algorithm to a cycle here. Yeah, you can try because the solution should be one segment on the cycle. Okay, so this problem can solve in linear time on cycle. So another possible generalization like here. This called a single attacking model. We define the cost here and the profit here. If we change the cost as time, it means we have to attack the system as soon as possible. Okay, so our goal, okay, is to attack the entire system as quickly as possible. So because the cost is time. Okay, because we have to attack the whole system, so the profit is doesn't matter. Okay, it doesn't matter. Okay, so we only have to count the cost we have to pay. Actually, the time we have to spend. So in general, the minimum cost, if we want to the whole system, the only we call this single attacking model. The minimum spanning tree should be the minimum one. Okay. So the problem is interesting if we consider multiple attacking model. For example, K attacking teams. Let me give you an example for K equal to 2. Okay, for maybe team 1 clear here and the team 2 clear here. So how to charge the cost? The cost is the maximum one. We have to attack the T1 and the other for T2 because the cost is time. So the maximum one is the bottleneck. Okay. So this problem we call the minimum spending k-forest problem. We are given a graph, an integer k, and a cost function C on E. The problem is to find a spanning k-forest of G such that the cost is as small as possible. Okay. So of course it's a bottleneck version. You use the min-max. It's called the min-max problem. Okay. So if I have to remind you that if k equal to 1, minimum spanning tree is the solution. Okay. So how to prove this problem is hard. This part is easy. Okay. We only have to find a possible reduction for equal to 2. We call it k partition problem. When k equal to 2, we have a set of positive integers. We want to partition them into two sets, k equal to 2. Okay, so such that the summation for each part, for each set is equal. Okay, so we can make this reduction. This is an instance of the two partition problem. So we want to partition two subsets, okay, A and B, so we can reduce to this bipartite graph. Let me show you an example here. Okay, it's a complete bipartite graph because k equal to 2. So this we have two vertices on the upper side, the other on the downside. So if we can find a solution for this problem, because k equal to 2, we can find, we have two teams to attack the whole graph. Okay, you can see the optimal solution here because the largest time we have to pay is the minimum. Okay, so we can obtain this solution, and this solution can answer the partition problem. Okay, so this problem is NP complete on bipartite graph. On the other hand, we can also do a similar reduction from the k partition problem to called a split graph. But anyway, I can show you this in this example. We have n integers, and we create a graph here. And this part is called form a complete graph called a clique. This part is an independent set. So because the complete graph, every vertex here, they can connect to the other vertices. So we can find, if we can find a solution for our k-forest problem, okay, so we can find an answer for the partition problem. Okay, so this is another possible reduction. Okay, so anyway, we can show that this problem is NP complete on split graph. Okay, so how to solve this problem for some special case? Okay, I just show you two straightforward example. One is on tree. For on tree, okay, if k equal to 2, we only need to remove one edge, then check which one is better. Okay, and yeah, so this one can be done in polynomial time. Okay, also we can consider a unicyclic graph. Unicyclic graph means it's a tree with one additional edge. So there is a cycle, only one cycle in this graph. Okay, so if this problem on a unicyclic graph, we only need to remove one edge on cycle and another edge on the remaining tree. Okay, so we can obtain a solution. Then we check which one is better. Okay, so this one can be done in polynomial time if k is fixed. Okay, so finally we can have a conclusion here. What is the approximability for the proposed problem? We know in this paper, they show the original problem. There is a 1 plus or minus epsilon approximation schemes. But what is the approximation possibility for our defined problem? Okay. Another maybe we can find some spatial graph that can be solved in polynomial time for our proposed problems. For example, interval graph and co-graph. So thank you very much for your